Boa tarde a todos, bem-vindos ao seminário do Departamento de Geofísica dessa semana. Apesar de ser em inglês, o Pablo, que é o nosso convidado de hoje, ele entende bem português também, então por isso que eu vou fazer essa apresentação em português, tá? Então, bom, apresentando aqui o nosso convidado, Pablo Nuñez Demarco, um pequeno background nele, ele fez a graduação na Universidade de la República, no Uruguai. Ele se tornou professor lá na mesma universidade, ele é professor... Eu estou aceitando o convite. Ele é professor lá e está fazendo a tese dele de doutorado na Universidade de Buenos Aires. Ele deve terminar agora no início de 2022. Bom, conheci pessoalmente o Pablo também, a gente coletou dados MT em, acho que foi 2015 ou 2016 no Uruguai, a gente tem trabalho junto. Então é um prazer recebê-lo, Pablo. Antes de passar a palavra para ele, só lembrar que no final a gente tem uma sessão de perguntas e respostas, vocês podem escrever lá no YouTube, em português ou em inglês, eu repasso para ele. E é isso, então, muito obrigado. Obrigado, Pablo, por aceitar o convite, pode ficar à vontade.
Obrigado. Good afternoon, everyone. Thank you for the invitation for this, for present my work in this seminar. As Gabriel said, I'm doing my PhD in geophysics in the IGeBA, the University of Buenos Aires. I'm working with potential field methods and magnetometry and gravimetry. And today I will talk about one of the methods I work with. I will start the presentation. There. Okay. Oh. Okay. Okay, I will present one of the methods I'm working with. In particular, about this paper we published last year during my research about the spectral methods. These spectral methods are based in a pretty simple theory. Rocks, I can summarize all the theory in this figure. We know that rocks are somewhat magnetic. They have magnetization, and they generate a magnetic field. And we can study this magnetic field, this magnetic anomaly field produced by the rocks by maps obtained by terrestrial, aerial, or satellite surveys. What we are doing with the spectral methods is to analyze the frequencies in these maps and generate by Fourier transform, and converting with Fourier transform this signal to the space domain into the frequency domain. So we obtain the spectrum of the signal, of the magnetic signal in the area. With this spectrum, we transform it to obtain the power spectra, and then the power spectra is later transformed into the radial, we average it radially, so we can obtain a 2D plot. What we do then, we have different theoretical models. Here are some representation of the different models we have. And the simplest one are models that we have chosen with a simple line in this power spectra. And we can obtain with these adjustments or with curves or with more complex models or theoretical curves of this spectra, we can obtain the geometrical parameters of the magnetic layer or magnetic sources we have in the terrain. In particular, we can obtain the data about the distance to the top of the magnetic bodies or the distance to the bottom of the magnetic bodies. Here, are two terms that will appear a lot in my presentation. There are Z sub T and Z sub B, the depth to the top of the magnetic bodies and the depth to the bottom of the magnetic bodies. This is even more complicated. We can complicate this method even more. We have an area with a magnetic field, and we can divide this area in different windows, little windows, and calculate this and make this calculation of the spectral method in each window. So we can have a data of the depth of these magnetic sources in each window. We try to this window overlap a little, so we can have information from both. In this way, we can obtain a kind of map of the topography of the magnetic sources. Well, this method actually can be applied to gravimetric field and to the magnetic field. It's more interesting when we apply it to the magnetic field, because the magnetic field has some particularities. With the magnetic field, you know, with the depth in the Earth, the temperature increases. And at some point, when we reach 500 to 600 degrees, the temperature is high enough to overcome magnetization, and magnetization disappears. This is called the Curie temperature of the minerals. So at some point, magnetization of the rock disappears in the Earth. This temperature limit is roughly the crust mantle limit. Here. It's not exactly, this is an oversimplification, but the basic idea is this, is that we can measure in some way the thickness of the crust using the magnetic field. Obviously, there are variations. There is not so simple. There are volcanic areas where the temperature is high and things like that. But the method, the basic idea is this. This is what made the method so popular. But it's not so easy. When I started my PhD, my advisor introduced me to these methods, to these spectral methods, and the software I need to use for each part of this process. And I realized that I was a lot of work. I have to work by hand in several places, and that this work would take months. So I said, no way, I will not do this by hand. I will make a program who does this automatically. So I jump into the programming totally unaware of the journey ahead. The method is not very complicated. So I just finished the basic programming in 2 months. But you know, when you make a program, it is necessary to know each variable, each condition, all the details. And that becomes a big problem. So I started reading a thesis, a book, a paper, 2 papers, and things were not so simple as I expected. A lot of complication appeared. So I ended up reading more than 100 papers on the subject. And finally, my notes become a revision of the method. Today, I will going to explain you a little about this revision, a little about this, not only about this method, about the problems I found in this method, and that even transcends this method. Our problems are present in all the geophysics and in science itself. First, I will present a more detailed explanation of this method with a little math. so you can understand a little better what I'm going to talk about. And then I'm going to talk about the problems I found in these revisions and some solutions, results that I found. Here we have a layer of magnetized layer in the Earth of rock, magnetized. We assume that this layer is magnetized with random magnetization. We have some geometrical parameters that define this layer: the top, the depth to the top of the layer, the depth to the bottom of the layer, Z sub B, and the depth to the centroid of the layer, Z sub 0. The general formula for simplified for the most basic model, I will present the most basic model here. The general formula for the the power spectra of a magnetic field for this layer is this equation here. Its equation involves the depth of the top of the layer and the depth of the bottom of the layer. And it involves n here is the wave number when we transform from the spatial coordinates system or data. It transforms in wave numbers, in spatial frequency. And we have a constant a. This equation can be simply solved if we apply logarithm at both sides. The term here in red, this term when n is high enough, is medium and high numbers of n, this particular number tends to 0, this tends to 1, and the logarithm tends to 0. So this term becomes negligible when n becomes high. So this equation can be transformed in a simple line equation when n is high enough. This is one of the equation, one line that we can adjust to our power spectra and then obtain with the slope of the line simply the depth to the top of the layer. Another thing we can do, another simplification, we can transform this equation here. We can develop, so we can make to appear the term of Z sub 0. And we can make use the first Taylor series of this part here in red. And so we can simplify it here when the wave numbers are close to 0. And then we obtain another equation of a line also. And we can adjust a line, so to the spectra, the power spectra divided by the wave number. And we can obtain the depth to the centroid of the layer. The depth of the bottom of the layer can be simply obtained by another, the relations of the two equations. Now we have these three equations, pretty simple equations. So we have the magnetic field of the area. We can calculate the Fourier transform, the power spectra, the radial aberration power spectra, and we only need to choose two simple lines to different parts of the spectra. And we can calculate the parameters of the magnetic bodies that generate this field. This is in principle pretty simple, and that is one of the advantages of this method and the popularity of this method. Now it has their problems. When I started to read it, one of the problems was I need to make a program to do this. So for the program, you need to know exactly where to measure. What are the ranges of wave numbers where I need to measure this? So I went, as everyone, to read the main material, the source material, the books, the papers who define the method. And they say simply that I should measure in high wave numbers or in low wave numbers. No more information. This is not very physical. I remember my classes in Physics 1. If I said something like that to my professor, she will tell me immediately what is high, what is low. We need numbers in physics. We need a range, that something who can we measure. This is not very exact in science. So I went to read papers to see if someone published where I should measure. And I found very interesting things, very interesting problems. You can see here, this is some from 2 different papers. This is from one paper, and in 2 plots, they calculate ZT and Z sub 0, and both are calculated in the same wave number ranges. This is a problem. I will censor the names of the authors of the papers. I will not intend to expose anyone here, but I will leave this in this way. But this is kind of odd. Theoretically, I show that some equations is valid for low wave number, and other equation is valid for high wave numbers. How is possible we measure both in the same place? This is from another method, from another paper, who applied this method for different windows. Each of these lines are the region in which they measure, these authors measure the wave numbers in these papers. As you can see, sometimes they are very different, and sometimes they are almost the same place. The same wave numbers are used to calculate both variables. This is kind of odd. This is also something that happens here that is common. People do not always measure in the same place. They measure in different places according to the form. They make this by hand. There is no an automatic procedure to do this. So everyone measures in a different place according to the form they see in their spectra. What is worse, but that was only the tip of the iceberg. I found papers, not one, not 2, many papers that measure both in the same curve. Both Z0 and ZT in the same curve. As you saw in the equations are not the same. Are not the y-axis is not the same in both equations, so you cannot measure both in the same curve. However, there are a lot of papers that measure it in different ranges, yes, by first time, but in the same equation. So this is very problematic. This was very problematic. And this is only the tip of the iceberg. Only 8, I review about this basic method. I review 72 papers. I read 72 papers. Only 8 explicitly report where they measure it. Where they measure is only 8 of 62 out of 62, 72. In 42 methods, I could extract some information from the plots. However, some papers only present some plots, some information, some examples of what they do. They analyze a lot of data. They show you an example, not all what they did. So, and we only have partial information of what they did in their works. What I can say, observing these papers, is that they measure in these ranges the wave numbers. Z0 is measured in these regions, and ZT is measured in this region, and the preparation for measure both is this one. In other words, they measure Z sub 0 and Z sub t in the same places. So it took me a year of reading to realize that I could calculate where to measure it. I have the theoretical curve. I have the adjustment curve, I can plot both and see where they adjust, where they are the same and where they not. Here we can see that these curves, these two equations, adjust very well in some region and do not adjust in another regions, in specific low region of wave numbers. So I made this for set T and also for set 0. Here we can see the curves adjust very well for low wave numbers and very bad for high wave numbers. So this is a pretty easy form to see where we should do our adjustments, in which regions is valid to make it, because it's the validity region we have. So what we presented in the paper was this image here. We calculate every possible combination of depths of both set 0 and set sub t, and calculate where they adjust or not, and where we should measure. Each here at the right, we have adjustments like the first I showed you. And what we have here in these color graphs, each line, each horizontal line here represents one of these adjustments. The pink area is where the curves adjust well, and the black area is the area where the curves do not adjust well. This is the slope difference, the percentage of the slope difference. So we determine the region where we should measure. This is the wave numbers here in pink where we should measure our data. We did the same for z sub 0, and we find the area close to the 0 where we should measure z sub 0. This is on the paper. The important thing here was when we analyzed what the people did, and we found that only 30 out of 68, 44% of the articles in the calculate z sub t in the appropriate wave numbers. And 21 out of 68, the 30%, calculate z0 in regions that are right, but includes regions that they should not measure. So it's kind of not so well. Only 26% were calculated. Sorry, this is in inverse. 26% did not calculate correctly and safely this the z sub t. In opposite side, z sub 0, only 3 out of 63 articles calculate z sub 0 in the pertinent wave number region. This is a disaster. Literally, all the works that use it and calculate z sub 0 are wrong. Five more calculate a little in a region that is a little more big and can be considered right. 88% of the articles measure it in the wrong region. I mean, in the region where this adjustment is not valid, when this theoretically is not possible. But as I say, this is not all the iceberg. This is only the tip. The things become worse. You know, wave numbers can be measured in radians over kilometer or 2 bits over kilometers. These are the unit system we use usually, or also in cycles over kilometer. We have also the spatial frequency that is measured in 1 over kilometer. The problem here is that radians and cycles are dimensional units. So both can be expressed as 1/kilometer. This is a very no problem. I invite you to read this paper of Moho and Phillips about dimensional units in the international system, because this generates a lot of problems. Because the units itself are the same, but the unit system itself it's the same. The dimensions of these units are the same, but they are not the same scales. They are very different. So this is problematic. Usually there is a sort of consensus here. There's a sort of agreement that cycles over kilometer are called 1/kilometer, and radians over kilometer are radians over kilometer. But it's not. There is no rule about this. The problem here is not only this can lead you to confusions, but is that the equation change depending on the unit system you choose. If we use this equation, we are in radians over kilometers. If we work with cycles over kilometer, we need to add 2p here in the equation. Now, when we go to the papers to see what happened, things become odd again. We found papers that present equations in cycles per kilometer, but then they show plots in radians over kilometers. Papers to show you equations in radians over kilometers. However, in the text, they say that the wave number is in cycles over kilometer. That is what they show in the plots. And that's what's happening here. This is intentional, or this is a mistake. If this is a mistake, it's a terrible mistake, because you have a factor, 2p factor of error in your results. And 2p factor of error in a depth calculation is a lot. There's more. This paper here is beautiful. You have here frequency in kilometers per second. This is a velocity. These units is, I don't know. I don't know how this was published, but it's beautiful. It's terribly beautiful. This thing happens. It happens a lot, and talk about several problems. This is not only this method. What is allowed. In this method, we can see another thing. Here, the authors measure in different regions the slopes of the curve. This is also known. This is not an error. What is an other error in this article is that we don't know if they are calculating z sub t or z sub 0. They don't say that. So we don't know which equation they are adjusting here, but they adjust several depths. This is very common. The idea behind this is that if you have different layers in your area, you can calculate different slopes and see the depth of the different layers. However, if you read the theoretical basis, the theoretical works that started this movement, they say that that's not possible. All the spectra is the average of all the spectra of each layer, and you cannot calculate the depth of any individual layer by the slope of any part. What we did in our paper was to generate different models, and what we see here is the spectra of each layer of the model, and in black the average spectra of all the layers. And here in the plots below, we see what we do is to calculate the slope for each segment, segment of the curve. for each curve. So we see, for example, here we have a layer of 5 kilometers, the red layer, 5 kilometers and 10 kilometers of depth. The set T is 5 kilometers, and we see that the depth in the right region, this white region here, converge to 5 kilometers. Now the blue region converge to 10 kilometers, which is the depth of the top of this layer. The depth of the green layer converge to 20 kilometers, which is the top of this layer. Now the sum of all the layers converge to the top of all the layers. In this case, in the other models, it converged to something between the second and the first layer. And the third model, they converge perfectly to the top layer. And the fourth model also converge to the top layer. But the bottom or the centroid of the layer, it's not the centroid of any layer. Depending on where you measure it, you can obtain almost any result. If you measure it specifically in the right region, you can obtain values that are very high, even deeper than the expected. Even, for example, in this model, the region, the depth is very high if you calculate, and it's wrong. So this theoretical model that you can obtain different depths, measuring different slopes along the curve is not right. Moreover, we have another problem. When we calculate the Fourier spectra, usually, and this is made in a lot of other areas of physics, when we calculate the Fourier spectra, we need to apply some methods to correct some defects. Fourier methods assumes that the figure we enter is perfectly symmetrical and continuous in all directions, but that's not true. So we need to sometimes apply some methods we call windowing functions and sum up to the spectra to calculate the spectra. Another options we have, another methods we use are extend the image in the area and generate some kind of slow step here to avoid these steps here, so we can calculate the spectra easily. Another solution is to mirror the image. This requires a lot of computational power. It's easy, but it requires to quadruplicate the size of the original image. But that is perfectly symmetric in all directions, so Fourier transform works very well with this. A fourth solution is to apply what we call the multitapper approach. We apply several windowing functions, and we sum up the frequency, the Fourier spectra of all these functions to obtain the general spectra. And here's what I mentioned at the beginning. The Fourier transform assume that our image is symmetrical in all directions, and they found these steps here or here, and they appear in the spectra. I don't know if you can see it well, as lines that mark our spectra. This can distort, all these methods can distort our spectra in some ways. Not doing nothing implies that there appears some frequencies in these steps that we don't want. To apply these window functions also imply to generate low wave frequencies that affect our signal. In fact, this is not in this paper, which is something we are publishing now. We test all these different methods Each color here in the plots are one of these different methods. And what we try to do here is to calculate Z sub t and Z sub 0 for different window sizes. We have an area and we try to calculate with different sizes of window our result. And what we saw here is that with big windows, we have better results. That is expected, this. But that also all the methods converge with the big windows. Some methods are better than others to calculate with windows, very little windows. With Z sub t, we do not have so much problem. This is one model and this is another model. The real value here is 5, is the line, the red line here. And what we see here is that for Z sub t, the top of the layer we are calculating, the error is not so much. It's only 0.5 kilometers. It depends on the application. It can be a lot if you are making a drill hole, but it's not so much maybe for a geophysical experiment or for a simple approximation of some body, or the position of some body. 500 meters is not so much. So Z sub t is a very, very accurate. Here also is in 5 kilometers. And all the methods has almost the same result. However, when we calculate Z sub 0, everything becomes crazy. We have some methods that are very well, perform very well, and we have some methods that are a disaster. This blue method here are these methods I showed you here, this Windows extension. Curiously, this is the fact that by default, some software do. For example, Oasis Montage software made this extension by default when you try to calculate Fourier transforms. And this extension is the worst for calculating Z sub 0. And this has sense because extend the windows generates long wavelengths and affects the wave numbers you are interested in for deep structures. For this other model, they perform also regularly, and we have not so well adjustment as with this one. Things are not so well. So here we have something that we are presenting and studying in this new paper we will present in a few months. And we found this also a problem. And you know what's the problem here? People do not usually say what they did to their windows. People do not report what they are making in the investigation. So we don't know if you are not using anything, if you are using a tapper function, if you are using an extension, people do not say. This brings me to the end of our presentation with a few concerns about these problems. What I presented here, the problems I presented here, are not only from this method, are common to several methods in geophysics. And beyond geophysics, things like this are present in geology, paleontology. I work in paleontology and geology and geophysics, and I have seen this kind of problem in all the areas. Some of them are theoretical, some of them are methodological, some of them are about revision of the articles. Obviously, this kind of errors not only is responsibility of the authors of the investigation. You have editors and a lot of reviewers. I mean, I review 100 of papers, and almost everyone has some flaw. This means that you have 100 of scientists and hundreds and reviewers that do not review it properly, the investigations. This is a kind of problem. The other problems that are here are one of the strengths of our foundations, of theoretical foundation. We neglect sometimes the study of the basics of the methods. It's incredibly how many people use methods that they do not understand really. And we need to understand the basis of our methods, the conditions in which they are valid, and everything. We trust. We have blind faith in papers we read, and we need to have more concern about this. Revision is a good thing, it works, but not is perfect. So we can find things that are not right, and we need to be aware that can happen. Another problem is this happens especially in geophysics. Geophysicists are a very heterogeneous group of scientists. We have geologists who has little or no knowledge in physics. We have physicists who have little or no knowledge in geology, and problems arise because of this, and we know some of them. And we need to work more close together and be worried about the areas we are weak and work more together with others who knows better these areas, maybe. And another big problem, what's one of the most important problems I found, is the reproducibility. It's supposed that the scientific method, that our investigation or research must be reproducible. We need to give enough information to others to make, so they can make our experiment again. So can they reproduce what we do? However, in the majority of the papers, people do not give enough information to do this. They don't say where they measure, how they measure, what process, what pre-processing they apply to their data. This is incredible. This is incredible how big is this problem. And we need to be more serious about our methodology and our theoretical basis of the methods we are using. There are a lot of errors in geophysics. We are publishing another papers about another methods today, and I think it's very important for us to be prepared for these kind of things. Well, I think I talked enough. I will give you, or if someone has a question or something about this.
Obrigado, Pablo. É muito interessante sua apresentação. Vamos ver se alguém tem alguma pergunta no YouTube, ou quem quiser falar aqui diretamente também pode ficar à vontade. Essa última figura que você mostrou você fez diversos testes com diversas formas antes de aplicar transformar de Fourier, né?
Sim.
Você mostra aquelas curvas. Aquelas, acho que mais quentes, né? Vermelha, laranja, davam resultados muito bons, né? E qual que era? Ou isso vai estar no paper?
Isso vai estar no paper, mas são em alguns casos, são as Tapper Windows. O melhor até agora é o Multitapper. Mas, às vezes, não fazer nada tem melhores resultados que fazer alguns. Isso é incrível. Não fazer nada tem quase os mesmos resultados que o Multitapper.
Tá.
Então, isso depende muito, aqui, o que nós vemos aqui isso depende muito das frequências que você quer estudar. qual é o método para isso? Porque para as frequências altas que você busca no set sub T, ele não precisa, não importa muito o método que você use. Não afeta muito as altas frequências, os altos números de onda. Mas, para as baixas frequências, os métodos afetam muito. E, às vezes, incluso, a gente aplica filtros aos dados e filtra essa parte do espectro que se precisa. A região dos números de onda baixos. E é a região mais sensível, ao ruído, do noise, e também é a região mais sensível à aplicação de ventanas ou os cálculos que vai fazer.
Uhum.
Hay que ter muito cuidado com essa região.
Tá bom, interessante. Avisa quando o paper sair, pra gente ficar atento. Deixa eu ver se teve alguma pergunta. Não, o YouTube não teve. Marcelo, pode falar. Sim.
Esse método é antigo e é muito usado.
Muito.
Como que se explica que é usado tão erradamente há tanto tempo?
Porque acho que a gente tem fé cega no que o outro fez. Então, a gente toma o paper e reproduz o método como o outro fez, mas não para ver o que está fazendo. Então, eles repetem os erros dos outros. Ou há questões como, por exemplo, esses métodos foram apresentados por o Tanaka, o Saki, e eles não dizem na região que eles mediram, mas eles mediram corretamente. Algumas, você pode ver nos seus papers que eles fazem o trabalho bem, mas a gente que repite o trabalho não presta atenção às condições no que tem que ser aplicado, então erram também nisso. E também na revisão, a gente aparentemente não revisa apropriadamente, não tem controle apropriado do que os outros estão fazendo. Não sei se é que a gente não conhece o método, que a gente não quer revisar bem ele, mas há erros aqui que são muito notórios. Poner uma frequência com unidades de velocidade é um desastre. O editor teria que haver notado isso, mas ninguém notou. Nenhum revisor, nem os autores. É muita gente aqui que está envolvida nesses problemas. Há outros erros que são mais sutis. Quizás sim, você requer alguém que conheça mais o método, onde você vai medir a região, mas há muito... Acho que nós ficamos muito preocupados por publicar mais novos dados e ter mais informação e ficamos desatentos às questões mais simples, as básicas, os fundamentos dos nossos métodos. Nós quase não aceitamos que a gente publique questões de revisão básica das metodologias. Isso encontramos que é chato demais, que não é necessário. E, às vezes, fazendo isso, descobre um montão de problemas que há e que ninguém notou. Porque isso faz 40 anos que está lá, alguns artigos desses, e ninguém notou que havia erros neles.
Outra pergunta é, frequentemente eu vejo a interpretação da curva de potência, onde se escolhe os trechos retilíneos, mas, às vezes, frequentemente eu fico com a impressão que essa escolha é muito subjetiva. Parece que a pessoa escolhe de tal maneira que o resultado seja
Sim.
o que ele quer.
Isso foi um dos problemas que eu encontrei, que você pode selecionar a região que você quer para que dê o resultado que você quer. Isso é incrível. O problema é eu queria fazer o programa que fizesse tudo automático, então eu tinha que colocar uma região específica e que tudo fizesse o mesmo. Mas o que acostuma fazer a gente é ver o plot, ajustar na região que eles veem que é linear, não na região que é correto medir a linha, fazer o ajuste. Mas isso é um problema. E isso é algo que a gente faz, e a gente repite, e aí você tem os erros repetidos no tempo.
E de que maneira que se pode usar, então, essa curva? Ou não dá para usar? É tão difícil de interpretar que
sim,
ela não é útil?
Para o topo das fontes magnéticas, é bom. É muito bom o método. Para a base das fontes magnéticas, é problemático. E pode ter muito erro. Você tem que controlar a região correta no que tem que medir. Medir nessa região, mas tem que fazer ali tem que discutir muito o resultado, porque pode ter muito erro. Tem que ajustar talvez com modelos ou com outros dados de outros métodos para ter segurança de que isso é correto. Na verdade, a base da fonte magnética é quizás o cálculo mais complicado. Sim.
Tá bom. Mas você poderia também usar a curva para fazer modelamento direto, né? Mais para testar se o seu modelo está razoável, não?
Sim, eu apresentei aqui só o mais simples, mas há modelos mais complexos. Você pode usar toda a curva. Há incluso modelos que assumem uma distribuição da magnetização fractal, que há muito mais complicados, implica na aplicação de mais variáveis. Eu estou trabalhando agora com um método que ajusta também com toda a curva. Tem seus problemas, você requer mais poder computacional, né, para isso. Às vezes não é tão fácil, mas eu estou trabalhando no ajuste do método que funciona, combinando métodos, está funcionando bastante bem. Mas você sempre pode complicar ainda mais o método, mas tem que ter segurança também de que as condições são corretas. No meu paper, eu reviso todos os métodos, inclusive os mais complexos, e tem também seus problemas nos ajustes, nas condições que eles asseguram que devem ser cumprir, há questões teóricas que não estão bem definidas, então há que ter muito cuidado também com isso.
Tá bom, obrigado.
Obrigado, Pablo. Realmente são duas coisas, né? Tem a parte do método e realmente a outra que é o papel dos revisores, né? Realmente
Sim.
É interessante, é algo para a gente pensar, né? Como que a gente revisa, quer dizer, essas coisas passam por cima, né?
Há um montão de coisas aqui para reflexionar.
Pelo menos quando eu fui começar a trabalhar, eu lembro que ia fazer transformada e tal, tinha que escolher algum meio de suavizar as bordas, né? Quer dizer, qual que eu escolhi? Eu, na época, espelhei, mas sem critério, não sabia exatamente se ia dar diferença, não, né? Então,
sim.
Porque não é uma coisa que você vê descrita, né, nos trabalhos, né?
E ninguém me estuda as variações que tem. Aí tem um estudo para fazer de qual é a diferença de usar diferentes condições. São coisas que a gente não faz habitualmente, mas são necessárias.
Sim. Tá bom, Pablo. Acho que não tem mais pergunta. Muito obrigado por ter aceitado o convite. Obrigado a todo mundo que assistiu e participou.
Obrigado a vocês.
Richard, pode parar.